Okay. So, good morning. Welcome on a presentation about somewhat controversial topic of JavaScript cryptography. I'm Krzysztof Kotowicz. I'm a web security researcher. In the past, I was researching HTML5 vulnerabilities and browser extension security. I was a pen tester at Cure53 company. Now I'm an information security engineer at Google. And this presentation will mostly cover research I was doing while working at Cure53. Two important disclaimers. The first one is I'm not here to represent Google, so every sentence I'm telling you represents my opinions, not one of my employers. And there will be no 0 days, so every vulnerability discussed here is already fixed or is publicly known already. So maybe let's do a quick show of hands. Who of you thinks that JavaScript cryptography is a good idea? Okay, there's a few hands. Who of you thinks that it's a bad idea? Yeah? Well, you can actually Google it pretty easily. It's a terrible idea, at least if you Google it. So there's two prominent blog posts about it from a few years ago. The first one by Thomas Ptaszek, entitled JavaScript Cryptography Considered Harmful. And the second one by Nate Lawson, final post on JavaScript Crypto. And if you take a deeper look at those blog posts and other opinions on JavaScript cryptography present in the, say, security or crypto community, you can derive multiple arguments. So why is it a bad idea? First, it's not needed. Because in order to do some computations in a web application, do some computations on secrets, let's imagine, I don't know, AES encrypting. You first need to deliver the code to the application, to the client, and only the server delivers the code. So server has the possibility of tampering with the code or backdooring the code itself. So any sort of computation being done client-side implicitly gives the trust to the server. And also, you need an SSL or TLS encryption anyway to deliver the code and prevent man-in-the-middle attackers to tamper with the code. So if you already have a secure channel between the server and the browser and you trust the server, why doing the computation on the client in the first place when you have much more control over the environment server-side? So it's not needed, usually. Also, it's dangerous. One of the most prominent things with JavaScript or web security is XSS. So exploiting an XSS vulnerability basically can backdoor any sort of computation done in the same origin. So it's dangerous. And also, it's hard. So the JavaScript language itself does not give you much features needed for cryptography. Say there's no big integer, native big integers class. And also the quality of the libraries there when the blog posts were announced was pretty poor. So you can imagine that JavaScript crypto is doomed to fail. So developers read the articles, asked about opinions, and stopped doing JavaScript crypto, and we all lived happily ever after, right? Well, actually, that was not the case. Now we have multiple cryptographic libraries available. There's crypto primitive libraries, there's some protocol implementations like TLS stack, there's multiple OpenPGP implementations done in JavaScript, there's user applications built upon those protocols, there's custom crypto protocols, so there's a lot of actual cryptography being done in JavaScript. From a researcher's point of view, this is an ideal situation because now we can analyze the code that is actually written and look at the vulnerabilities or problems with JavaScript cryptography that are based on real-world scenarios. This is not a theory. So I had taken a look at a few of those libraries, and I decided to take the following approach. First, I would analyze the code of those libraries, find the vulnerabilities that are actually present, not the theoretical ones. Look at the problems that the crypto is actually facing. Understand the root causes of those vulnerabilities that I found. Try to compare the situation to native crypto libraries. Fix what is fixable or propose fixes, and describe the limits of JavaScript cryptography. And this is what the talk is actually about. So if you take a look at cryptography vulnerabilities present in JavaScript libraries, you can divide them into two sort of buckets. The one bucket consists of problems that are present because of the features or lack of features within the JavaScript as a language. And the second bucket is the problem of basically web platform. So web platform gives certain restrictions or operates in a certain model that poses problems to doing crypto well. So let's take a look at language issues. But first, do we even care about specific language being used to code cryptographic, say, protocols? Does it even matter? Well, I would say it does. And if you think otherwise, you probably are going to fail. I repeat, you are going to fail. So, yeah, it does matter. Language features can pose problems, real-world problems, and there can be vulnerabilities because of that. So what is JavaScript as a language? It's a very tricky one. So it's a dynamic language. It's a language which is weakly typed. It's a language with sort of unusual inheritance model based on prototypes. It's a language with an implicit global object that also poses problems, and the parser is pretty forgiving. So if you take a look at just a short example of those problems, is that code is actually a valid JavaScript. It's an alert one. Obviously, you can derive all that. This is all being done on like type coercion being done by the language itself. So you can construct pretty much any code in JavaScript, arbitrary code, by just using six characters. This is just an example. The slides are not really visible here, but basically, there's a lot of gotchas in JavaScript or quirks resulting from the fact that JavaScript is weakly typed. So this is actually taken from the page called wtfjs.com, and there's multiple issues being described there. So I would encourage you to just go there and check how weird JavaScript can be. So one kind of a problem. So the Boolean true value is equal-ish to string true, but if you try to compare false to false, it's actually false. So it's not the same, right? Or for example, the minimum value is not actually less than the maximum value derived from math object. And while null is, or type of null is an object, so null is an object, it's not an object. So yeah, and there's multiple ways of triggering this weird behavior in JavaScript. As a result, developers actually, when coding applications, not only crypto applications, they don't use types in JavaScript in general. They don't use, for example, instance of. This is very rarely appearing in JavaScript code. And this matters to crypto. There can be real vulnerabilities occurring because of that. And this is one example of such a vulnerability. It was pretty famous, I think, last year or 2 years ago. So CryptoCat, an application doing encrypted multi-party chat in JavaScript, in browser extension, had the problems with the random number generator entropy. So when it was generating private key for user, which obviously needs to be secure, it does not, it needs to be long enough, the entropy needs to be big, from which the key is generated. So it used the CryptoCat random string library to seemingly generate a private key based on 64 random bytes. This is in a comment. But actually, if you take a look at the implementation of the function, it generates a random string of length size, so 64. But actually, because of the values of the parameters here, it consists only of the decimal digits. So it's 64 decimal digits instead of 64 arbitrary bytes. So the amount of entropy is way less. And this is all because of weak typing. I mean, if the developer had used like byte array, he probably would not have the problem that he was facing now. So because of that, because of this stupid mistake, but again, coming from the language features, he lost a lot of entropy, and there were several other issues with the entropy there, and the key was actually brute forceable by certain attackers. The other thing with JavaScript is magic properties. So again, let's take a look at CryptoCat. It's a multi-party chat application. And in order to communicate with someone, you need to exchange keys and generate a shared secret. So this is a piece of code that is run when you receive an initial communication from someone new in the multi-party chat channel. So it checks whether we already have a public key stored internally in a variable for this particular sender. And if we don't, there's an exclamation point here. So if there is no such a key yet, well, just assign the value coming from the wire and generate a shared secret for that chat member. And later on, when you decrypt the incoming message from this new or already known sender, you just check whether you have a shared secret already for the sender. And then you compare the HMAX and use AES to decrypt the actual message. And this one is obviously secure. I mean, it looks sane, maybe apart from this comparison of HMAX, which you should do constant time, but that's another problem. Unfortunately, JavaScript has a certain property that allowed the attacker to change the logic of the application. So there's a proto property of any JavaScript object, and this one, at least for the usual dictionary, like the one used for shared secrets or public keys, resolves to a new object, an empty object, and empty object is actually true. It's a truthy value. So public keys, proto. So if there's a sender called proto, let me go back to the slide. If there's a sender called proto, it would resolve to true. So you would never generate a shared secret with someone called proto. And then, if you checked for the shared secret, this would resolve to true as well. So you probably have a secret, right? And then you start accessing the secret. Here, shared secret sender HMAC. And this one obviously fails because shared secret proto is just an empty object. So the result of that was whenever someone called proto joined the multi-party chat, he broke the chat for everyone else. Again, this is only because of JavaScript feature. But this is not unique to JavaScript. Certain languages also have these kind of problems, like Python has magic properties as well, and you can do some attacks or influence the logic of the application through magic properties. So this is not really unique to JavaScript. The other thing with JavaScript is silent errors, and this one can be really dangerous. So if you try to construct an array and then access an index which is not yet present in an array, it doesn't throw any error. It just returns undefined, which is better than C, because C would basically allow you to browse like a memory range which is not available for this array, at least it wasn't defined there. So But the problem is, it just silently returns a value. And there's a second thing you can combine with that. So this is actually a Unicode character or code point. So in JavaScript, a string does not consist of bytes. It consists of Unicode characters or code points. So a string charcode add function returns a value which usually is less than 256, right? But if you supply a Unicode string there, actually the value will be greater than, it wouldn't fit in 1 byte. So there's a lot of attacks you can do with Unicode on JavaScript libraries, but I would like to describe one attack which is very relevant to crypto. It's a 16 snowman attack. It's an attack discovered by Daniel Dreschenbacher on the JavaScript AES library implementation. And it uses those 2 quirks of the language to form a really nice attack. So first, a little bit about AES crypto. How does it work? Well, it's a block cipher, multiple rounds block cipher. So you have a plain text. Then you perform operations with a key on that plain text. Then there's multiple rounds doing, I think it's 9 rounds in AES. So there's a few operations being done repeatedly on that plain text. And there's last round after all with just mixed column step is removed from here. But the important thing is, first, after you add the round key, you perform operations on SBox. SBox is just 256 hard-coded values for the AES cipher. So you perform operation on plain text with this SBox. It happens repeatedly. And you get the ciphertext. The decryption is in reverse. I will just describe the decryption later on. So this is the vulnerability. So if you supply a plain text which consists of Unicode characters, the subbyte function which accepts a state of the cipher. So this is basically in the first round. It's a plain text somehow modified, but it is a plain text. And an SBox value. This is, again, 256 hard-coded values. It tries to find a matching SBox bucket to replace the state, but actually this one is not 256 anymore. It does not fit in a byte. So it doesn't find any value in the SBox matching. So this call returns undefined. So after calling this function, you get a state from consisting of high bytes, let's say, or values that don't fit within 1 byte, and you replace it with just 200 or 16 bytes undefined values, 16 undefined values. So you lost the first state completely. So you basically kind of bypass the first round of AES. But there's interesting thing happening further on. So we have a state which is undefined, which would probably trigger some tricky things in the JavaScript. Maybe it will throw an error afterwards. But there's another function in AES implementation here which allows us to go back from the undefined to zeros. This is a mixed column step. And if you take a look, there's just a lot of XOR operations. And in JavaScript, 0 XOR undefined is 0, because why not? So after processing this function, after executing it, you get an undefined, XOR 0, which is 0. So after the first round, here, before adding the round key, for any arbitrary plaintext being done here, like Unicode plaintext, you would result in a state being 16 0 bytes. And then there's another round doing processing. But then we get the decryption process. So if you with the library, if you encrypt the Unicode string, you get a ciphertext, which is sort of modified because of that quirk. And then you try to decrypt the same string with the key that you don't know. And all the computations are being done in reverse. So at the last round, you get back the same zeros here. And after that, you call inverse subbytes and add round key. So inverse subbytes basically applies the same transformation as the subbytes function. It just processes the inverse S-box. It's a feature of the crypto cipher here. So basically, we have a state which is 16 0 bytes. And for every 0 byte here, it tries to access the bucket for the S-box, constants. And it always ends up being the first one, the first bucket, the 0 bucket. So you end up with the state being, actually the first value in the inverse S-box bucket is 52 hexadecimal. So you end up with the plain text, after all, being 052, 052, and after that, you just add the round key. You XOR the whole thing. So what you did by decrypting this modified ciphertext is you end up with just an AES key, which you shouldn't know, XORed with 052 bytes. So this is a simple inverse operations. Then you XOR the resulting plain text with 52 bytes, and you get the key. This is a beautiful attack coming from just the features of the language. But again, this is not just a JavaScript problem, or this is not a problem that only occurs in JavaScript cryptography. So there's similar things being done, or similar failures being done, for example, in GNU TLS, the vulnerability from this year. So what happened is, it's a TLS implementation. So when it verified the certificate of the server, there was this function called check if CA. And this function basically validated whether the certificate is being signed by the trusted issuer. And if so, it returned, as you can see on the comments, it returns true or false. Well, actually, it returns an integer here. In C, there's no exceptions. So usually, what you do to report errors, you return negative values. But the caller for this function only compared to 0. So whenever you were able, as an attacker, to trigger an error condition, which is pretty easy, you just supply, a certificate which is invalid in a certain way. This return value started being negative, like -1. And of course, this bypass this, the condition wasn't met here. So the abort step in the certificate verification wasn't being done, because it would only fail if the certificate wasn't trusted, but there was no error condition in between, like during the verification of the certificate. So again, you return an integer, but you treat the value like a Boolean, and this is the root cause of this problem in C implementation of TLS stuff. Looking back at the language issues, they are not unique to JavaScript. They are present in pretty much any language that you try to implement cryptography in. But you can overcome them. You can use the ECMAScript 5 strict mode, which disables a lot of quirks of the language. You can use a sort of JavaScript compiler, like for example closure compiler, which allows you to actually enforce the types being declared during the compilation. So it allows you to implement strong typing within a language which doesn't support it natively. Also, obviously, the development practices like code reviews, testing, unit testing, integration testing, continuous integration, they also immensely help to produce a code which has less probability of being vulnerable. But the more interesting problems to JavaScript cryptography are actually web platform issues. Because JavaScript is not an abstract language, like executing in some mindset, right? It's a very concrete implementation. JavaScript always runs within a JavaScript engine, and there's multiple engines right now. That language engine runs in an execution environment, like say a browser renderer process or server process, like Node.js, for example. There's also different APIs available to JavaScript code, like say DOM implementation, if it runs within a browser, web crypto for some browsers, a browser extension API, and so on and so on. So there's different things that the JavaScript code can actually call. Also, because of those environmental issues, there's different restrictions being placed upon the execution of the code. Like the most famous one in web is same origin policy. So you shouldn't do things that affect other origins or applications from other origins. There's like a block or policy that prevents you from affecting other origins. There's content security policy. There's iframe sandboxes, extension security policies. And all those policies actually affect any JavaScript program. And those conditions are actually much more important than the language issues themselves. The first vulnerability type arising from a web platform is obviously cross-site scripting. Well, cross-site scripting is all over the web, and you already know that. I mean, it's OWASP. But when thinking about JavaScript cryptography, we need to think of XSS in different mindset. XSS here is basically an equivalent to remote code execution, because that is what the attacker is actually doing. He's supplying the code which executes on a client, and that code can bypass certain security guarantees coded within JavaScript application. So what can XSS do for crypto? Well, almost everything. It can replace a random number generator, a very tricky attack. It can exfiltrate the secret key. It can replace the public key in asymmetric cryptography. And obviously, because XSS is such a, say, popular vulnerability, it also is present in cryptographic code. So when I took a look at Mailvelope, which is OpenPGP implementation in the browser or integration, it allows you to use PGP within Gmail interface. And there's usually when you implement something like this, there's a very simple attack which almost always works in the browser again. So you have a public key of someone, of your victim, and you can encrypt any sort of arbitrary message to the victim, right? So you encrypt a message called, with XSS payload basically, HTML message with some JavaScript code. And what Mailvelope did was, of course, it decrypted the message safely somewhere in the extension code. But then, in order to be user-friendly, it embedded the resulting plaintext back into Gmail interface. Because ultimately, that's what you want to do. You want to read the email in Gmail interface, in UI of Gmail. So through that vulnerability in the extension, obviously it used like email HTML assignments to achieve that, which is technically a DOM XSS vulnerability. So through exploiting this vulnerability in the extension, the attacker could actually execute arbitrary code in the context of Gmail. So I could read any other email, I don't know, set up email forwarding, exfiltrate contacts, whatever. Or make a URL addressing attack to kind of enforce the user or convince the user to reveal his password, whatever. But this is not bad enough. I mean, this only allowed the user to exploit the Gmail application. It didn't have access to the private key, for example, because it was separated by same origin policy. It was the computation over the ciphertext was being done in another context. So this was an interesting case, but not as catastrophic as the next one. So the next one is CryptoCat. Again, so in order to talk with someone at CryptoCat, you need a shared room, like a chat room, which is called conversation name, I think, in the code, and of course you need a nickname. So CryptoCat only validated the nickname upon entering it in the user interface. So you could copy the code of CryptoCat, remove that validation being done, and start a conversation with someone, embedding angle brackets and starting putting JavaScript code in there. And when you start a conversation with someone or join the chat room, the code would be trusted by CryptoCat extension and just embedded in the DOM of the extension. So what can you do with this? Well, CryptoCat had two versions of the extension. The one was implemented as a Chrome extension. And in Chrome extensions at that time, there was already content security policy enforcement. So the attacker could not execute JavaScript. But what the attacker could do is to embed any sort of HTML, say static code. So potentially you could only do some UI spoofing, maybe convincing user to type a password, something like this, like replacing certain messages and so on and so on. So the capabilities of the attacker exploiting that vulnerability in Chrome extension were pretty limited because of content security policy. But in Firefox, the matters are much worse. There wasn't any content security policy present at that time at Firefox extensions. And even worse, if you have an XSS in Firefox extension, what you can do is you can execute arbitrary code on the machine as a OS user, which I can install malware through that vulnerability by starting a chat with someone using the Firefox extension, Firefox CryptoCat extension. So you can imagine that XSS here is a pretty big deal, and this is much more destructive vulnerability for JavaScript crypto as well than the language issues like those weak typing, for example. But again, remote code execution is not unique to web platform. I mean, this is a vulnerability that cryptographic applications are facing year after year. For example, this year, you could exploit a GNU-TLS SSL client. So a server supplied an information to a client or sent certain byte with a long session ID and triggered a buffer overflow on the client side. And of course, there was a possibility of executing arbitrary code. So these kind of vulnerabilities, and I really encourage you to think of XSS in terms of remote code execution, because that's what it is. These type of vulnerabilities also exist in native crypto applications. Other type of issue coming from web platform, actually present in the code of the applications that I've looked at, is the usage of math random. Math random used to be the only random number generator available to JavaScript applications. The problem with math random is that it's not cryptographically safe, and you can recover the state in some browsers. You can even recover the state cross-origin, so by forcing the user to, in a second tab, if you are able to execute JavaScript code, you can trigger certain conditions which enable you to know this current state of the random number generator, and with that you can predict the computations being done on the second tab in a different origin. Right now, fortunately, this issue is kind of fixed, because we do have now in almost all of the browsers a native cryptographically safe pseudo random number generator. It's being done by web crypto. So there's this function you can call instead of calling path random. In Node.js, there's a separate function being available as well. But as it turns out, even when there's a code available doing cryptographically safe PRNG, people still use math random. For example, For example, in OpenPGP.js, this is obviously an OpenPGP implementation in JavaScript. There was an RSA encryption padding, according, of course, to the specs. And it used a pseudo-random function here to construct a padding for RSA. And this is actually essential to RSA security, that the padding being done here is generated or is unpredictable by the attacker. Another thing, CryptoCat, again, it's my hero. It's an XMPP implementation as well, and it uses a certain protocol called BOSH. And in BOSH protocol, there's a session identifier and request identifier. And these are, it is critical for them to be unpredictable and non-repeating, like anons. But CryptoCat used a Strophy library. So again, this is not a vulnerability in the CryptoCat itself. It's a vulnerability of a dependency that CryptoCat relied on, which is an interesting problem to security as well. But technically, through that vulnerability, you could exploit CryptoCat. So obviously, it used math random function, even though the safe alternative was already available. But again, is this problem only occurring in web? Not at all. Let's take a look at OpenSSL Debian fiasco. So in 2006, there was, the case actually occurred in 2008, so the problem was present in the wild for 2 years. So what was the problem? Well, OpenSSL, in order to feed the entropy to the random number generator, it uses multiple sources. And one of those sources is actually reading an uninitialized memory with the assumption that the bytes are, they can be anything, there's no control over it, so it serves the purpose well. But obviously, it's not a good developer practice. So the Debian maintainer for OpenSSL analyzed OpenSSL with Valgrind. It's a tool that checks for memory safety issues. And obviously, there were warnings being triggered because somebody is trying to access uninitialized memory. That's usually a vulnerability. But he didn't know the code well enough, so he asked the mailing list for OpenSSL developers, saying, hey, I'm running this with Valgrind, and these are warnings. What should I do? Maybe I should remove those, code lines triggering. And they said, yeah, possibly, there's no harm here. So he removed it. And as a result, the only entropy source was actually the process ID, which is way too small for seeding a random number generator. So SSH Keygen, which used OpenSSL library, on Debian for over 2 years, it could only generate only 32K possible private keys. So as you could imagine, at 2008, when the issue was made public, pretty much everyone had to replace their private key. It was similar to Heartbleed. Another kind of problems, timing side channels. So the thing is, in crypto, you can derive a lot of information from side channels. So you don't attack the crypto directly, you attack the effects that the crypto triggers. In JavaScript, it is very easy for the attacker to execute code which is pretty close in the execution environment to the application being attacked. You can even enforce the code to be in the same thread via using iframes. And Eduardo Villanava demonstrated an attack using iframes, exploiting timing side channel vulnerability that allowed him to cross-domain, brute force a number being pierced by the crypto code in a certain origin, in a different origin, by just repeating and measuring timing, measuring the timing differences. Timing side channels are present in real JavaScript applications. For example, this one is present in the OpenPGP RSA, the encryption and the padding. Again, this function should be side channel free. This is essential for the security of the cycler. So it should always execute in the same amount of time. Unfortunately, there's multiple return points. There's the branching being done here. So you can measure differences in time based on different input values to this function. But this is, again, not something unique to JavaScript. Multiple libraries are, or multiple code bases are vulnerable to the same kind of problems. For example, this year, there was a timing side channel in Java Secure Socket extension, which was able to exploit the fact that the TLS stack implemented by JSSE generated a random number only under certain conditions. The conditions where the padding is invalid. And only measuring precisely the time of that, you could construct a successful attack against JSSE. Other kind of problems, not really unique to JavaScript, actually not even coming from JavaScript, is direct memory access. So I guess you all remember Heartbleed. It was not a crypto vulnerability per se, but through lack of bounce checking, you were able to extract the memory of TLS server. So this allowed you to bypass the encryption promises being done by SSL because you backdoored the whole thing. Fortunately, JavaScript is a memory-safe language. We don't have any, memory initialization thingies. We don't have buffer overflows, so we're good, right? Not really. If you take a deeper look at the language, again, it's not an abstract language. It is being run in the JavaScript interpreter or compiler or execution environment. And this one is coded in native languages or non-JavaScript languages. And these can have buffer overflows. So there were multiple, even this year, there were multiple vulnerabilities in the JavaScript engines that allowed the attackers to execute arbitrary code. And this was not XSS, this is something deeper. You execute like a native code. This one was pretty cool. It was found by GeoHot. So what he did is he initialized an array buffer object and redefined the getter for the byte length property of this object. And it was a function which returned a pretty big value. So he simulated a really small array buffer which pretended to be pretty big. And through that, he was able to read and write arbitrary memory areas. So when you want to do cryptographic computations in JavaScript, the real problem that you are facing is not XSS, because that one is easy to solve if you have the control over the code. The real problem that you are facing is that the browsers are an attack surface for you as well, because the attacker might exploit the HTML parser, the JavaScript engine, the network stack, and through that, you can, for example, read arbitrary memory areas to, extract private keys of your application. And the problem with web here is that pretty much visiting any URL in any sort of tab can potentially execute the code that exploits those vulnerabilities. So what actually happens when you exploit say, HTML parser vulnerability in a browser? Well, in Firefox, it's kind of game over, because Firefox internally, it's a single process. So you can access the information all over the place. Like there's no process boundaries here. In IE, Microsoft uses multiprocess in implementation. And in Chrome, Google went even farther. So there is a separate process for every tab you are visiting. And there's also a sandbox. So whenever somebody exploits a renderer, he still executes code within a sandbox. So to say, he cannot, without escaping the sandbox, which is a separate vulnerability, without escaping the sandbox, he cannot read the memory from, say, another tab. So basically, if you are able to execute arbitrary code, you can think of it as sort of installing a malware on user's computer. And this is, again, not something unique to web platform. I mean, crypto software was bypassed by simply installing the malware. Like GNU-PG, even in the FAQ, mentions a case where like the security promises of GNU-PG were bypassed by the drug administration authorities by simply installing a keylogger on the victim's computer. So for JavaScript, you need to look at the browser as an equivalent of an operating system for native crypto applications. So browser security in this scenario is sort of equivalent to host security. Unfortunately, there's one difference, and the difference is the application delivery. So in order to run something on your computer natively, like say an application, a desktop application, you need to install it first. There's a certain process, and you need to download it of a certain code repository or something. In the browser, you can execute arbitrary code by just visiting the URL. So as you can see, it's much easier to exploit the browser than it is to execute arbitrary code on the machine. So essentially, the web platform is a huge code execution playground running happily any code supplied all through over it. And only same origin policy can sort of isolate the applications. And the isolation is required for crypto operations, as you can probably imagine. So is JavaScript crypto doomed then? Because if you create a perfect application, there's no XSS there. You can trust the server to not backdoor the code for you. You put it on a website, there's TLS with perfect forward secrecy, whatever. And you can still be backdoored by just anyone executing the code in a second tab of your victim's computer, right? And exploiting the browser. So how can we fix this problem if it is fixable? Well, only browser extensions can help you here. So browser extensions are usually executed in a separate process, at least for certain browsers, and they have a sort of isolation from other websites. So by moving all your crypto code to browser extension, you can have the sort of isolation as much as you can get that would protect you from exploiting the browser itself. They guarantee a secure signed code delivery because you basically install an extension. You don't just run it by visiting the URL. There's a separate storage area, and there's way better separation than just same origin policy. In Chrome, you also get the process isolation. So extensions are guaranteed to run in a separate process. Unfortunately, it's not a perfect solution. And the open problems are, well, your extension needs to somehow usually cooperate with the website. So you need to create an API for that. And this API needs to be secure in order, for example, not to trigger the XSS vulnerability or allow the attacker to, I don't know, replace the key by just, I don't know, allowing arbitrary website to call functions which should be restricted by the extension. And also, obviously, in Firefox, XSS basically destroys the whole security promises because you can execute arbitrary code there. Open problems. Well, we still don't have the mlog equivalent for JavaScript cryptography, so eventually the secrets can be swapped to disk, which is a problem. We don't have complete control over the execution environment, so even if we have a constant time code or constant time-ish code in JavaScript, the optimizer of the language can still do magic, and that magic may cause timing side channel to be possible. We don't have a secure story yet, though web crypto does promise interesting things here. And also the real problem is actually that the extension is silently auto-update now in the browser. So theoretically, you have a secure extension in the browser, but somebody forces the producer or the author of the extension to backdoor the code, and you get a new version silently, this sort of problem. And we don't yet have a full process isolation, so under certain scenarios, you can end up being executing in the same process as the extension. So the summary, JavaScript crypto, looking at the code, is way better than it used to be. There's still a lot of vulnerabilities, but these are, I would say, manageable. So the JS crypto flows mentioned before, like XSS, these are not real problems. The real problems are the platform issues, especially the direct memory access thingy and exploiting the whole browser problems. Yeah, and basically what you can do is move all your crypto code in the extension, because executing the code in the website side of JavaScript applications gives you 2 weak promises. It gives you 2 weak security guarantees, and there's just too large attack surface available to the attacker. And this is all. So I'm open to questions. Thank you. Yeah.
Sometimes Google announced its own extension called end-to-end encryption. So did you analyze it, and what is the result?
Well, I'm actually one of the team members of end-to-end. So yes, I have analyzed it. It's currently an open source. So basically, it's an open PGP implementation in JavaScript as a browser, as a Chrome extension. So yes, I have analyzed it. I encourage you all to go ahead and try it. It's under a vulnerability rewards program, so if you find any exploitable vulnerability, you can actually earn money off that. It's all open source, and we really try to make the extension as secure as possible. And we are aware of all the problems with JavaScript crypto, so we kind of learn from others' mistakes.
Why did you try to implement some, crypto tools in browser RP, not as JavaScript, not as extension?
You mean why did we?
Why didn't you implement some web crypto or something like that in browser to give?
Oh, because that's not the problem that we are trying to solve. Doing that in the browser certainly wouldn't earn a lot of trust in people, because Chrome is not open source, right? So there's still a possibility. It's not auditable. So, and with open sourcing the library, we encourage people to use JavaScript crypto even outside Chrome, outside any sort of our or Google controlled environment. And actually doing crypto implementation in JavaScript is advancing the field, I would say. It's something that we all needed in Google and outside of Google. So that's why we have taken this approach. Yeah?
I saw you talk about crypto applications, but there are also crypto libraries completely written in JavaScript, like the crypto library and the Bitcoin.
Well,
they are built by yourself.
yes, unfortunately they are pretty old and not well maintained right now, at least the Stanford one. So yes, I am aware that there are implementations of that, and I have no knowledge of any vulnerabilities from that particular pieces of code, but I would say we need more modern libraries, because now JavaScript gives you the possibility of say typed arrays, byte arrays, and web crypto, and that wasn't available at the time when Stanford library, for example, was created.
So, is it possible with current browsers implementations to create an NSA-proof extension for encryption? Like, so no Google and no everybody else produces.
I mean, usually it's not a. I mean, potentially, it's a philosophical question. I mean, you cannot trust anything ultimately because everything can be backdoored, like down to the level of firmware, the CPU, microcode, and so on and so on. So, if NSA or whoever has the capabilities of backdooring something down to the firmware level, well, no browser is going to protect you from that. It's just a, it's ultimately a question of how paranoid or how what kind of mindset do you have? What attacker do you want to be protected against, or what kinds of attacks? Yeah.
We've been looking into the server side, so I mean, Node.js, are there specifics?
I mean, JavaScript is JavaScript, so obviously you don't have the whole web platform issues. Let's say second part of my presentation. You still need to be aware of the weak typing issues of JavaScript, and actually Node.js gives you certain say native primitives which you can help you, like it has a TLS stack. So there's a lot of things already being implemented in native languages that you don't need to code in JavaScript because they are available. So I haven't looked deeply into Node.js, but I am aware that there's a good work being done on that front. Yeah.
Probably can write extensions in Firefox and Chrome. And how about Internet Explorer?
I haven't been researching Internet Explorer lately, so I wouldn't be able to give you an answer, but I wouldn't expect that to be really possible or feasible.
So you would like to use an extension. Like the web crypto API, which
Yeah, but web crypto doesn't give you everything. I mean, you still need an application using the web crypto.
you miss at least key management.
Yeah, and this is usually the problem in crypto, right? Where do you store the keys and so on and so on.
But you think that you have to write a web crypto in separate memory extension and not.
Yeah. I mean, web crypto is thought out as being just an API available to JavaScript. But
Supporting legacy browsers.
yeah, I know that.
The biggest problem with writing web applications and not secure.
Yeah, I mean, it is a legacy problem, like the problem with legacy applications, and it's software development problem essentially. So yes, we have certain features in modern browsers that allow us to finally have something much more safe or secure, but you have older browsers, and you just, if the browser vendor doesn't support the users, like stops updating the browser, stops adding new features to it, well, there's only so much you can do. Thank you.